So imagine you're trying to fix a minor rendering bug in your favorite video editor.
Yeah.
And you discover that to actually get your fix accepted, you have to navigate the unwritten social dynamics of a real-world fraternity of French university students.
Right, which sounds completely absurd.
It really does. But it highlights this fundamental illusion we have about software. We're so used to thinking of applications as these sealed boxes.
Yeah, you download a binary, run the installer, and just consume the product.
Exactly. And even if it's open source, you kind of assume the barrier to changing it is just technical, like you just need to know how to code.
Hmm.
But the reality of modifying software, of going from a consumer to a creator, is this wildly complex collision of, well, dependency management, compiler mechanics, and these completely invisible social graphs.
It really is a whole different world under the hood.
So today, we're cracking open that reality. Welcome to the deep dive, everyone. Think of this as a DIY masterclass in seizing control of your tools. We're going to get our hands greasy in the trenches, looking at how to manually crack open an open source code base, specifically the video editor Kdenlive.
And we'll look at the real-world realities, both technical and social, of compiling that code yourself.
Right. But we aren't stopping there, because we're taking this all the way to the absolute bleeding edge of software extensibility. We're going to explore how the Model Context Protocol, or MCP, is completely bypassing traditional plugins.
Oh, yeah, bringing AI agents right into the editing workflow.
Exactly. Going from writing raw C++ to orchestrating these massive cloud AI pipelines that can just generate and edit video based on plain English.
It's a huge paradigm shift because, this transition from manual manipulation to AI orchestration is really redefining what it even means to be a developer.
Oh.
But to get why that leap is so important, we have to look at the friction of the old way of doing things. I mean, before you can modify a complex C++ app like Kdenlive, you have to understand how it's packaged and distributed to your OS.
Right, because how it's distributed dictates how isolated the software is, which obviously impacts how you can integrate it with other stuff.
Exactly. And the KDE Discuss forums actually give us a really fascinating window into this. Users are having this massive debate about getting Kdenlive via Flatpak versus AppImage on Linux.
Yeah, and for a power user who's comfortable in a terminal, you'd probably just assume they use whatever package manager their distro ships with, right?
You'd think so. But video editors are notoriously heavy. They rely on dozens of external multimedia libraries. And the forum debate shows that the sandboxing architecture of a Flatpak actually creates severe bottlenecks for a creative workflow.
How so? What does Flatpak actually do to the app?
Well, Flatpak relies on namespace isolation.
Yeah.
So it basically constructs a virtualized file system and network space for the application to live in.
Kind of like a bubble.
Exactly. The goal there is security and dependency resolution.
Yeah.
The app runs against a known runtime, rather than whatever unpredictable libraries happen to be on the host system.
Makes sense for security.
It does. But as user Burndam and Jay pointed out in the thread, a video editor is not an island. Kdenlive is explicitly designed to talk to external animation tools like Glaxonomit, or audio processors like Audacity.
Oh, right. And if it's in a bubble.
Exactly.
Yeah.
When you confine Kdenlive inside a Flatpak sandbox, it loses the ability to see or execute those external binaries on the host system. You basically sever the inter-process communication.
Wow. So, I see the security benefit, but for a video editor, that isolation sounds fatal. If I want Kdenlive to send a clip to Glaxonomit to add a graphic, the sandbox is just acting like a firewall.
It really is. And it seems the Flatpak runtime approach isn't even bulletproof. There were reports in that exact same thread of the Kdenlive Flatpak just failing to launch entirely on Fedora.
Wait, really? It just wouldn't even open?
Yeah, failing on launch. So you have all the downsides of the sandbox, but you don't even get the guarantee that it'll work universally.
That is frustrating. Why does it break on Fedora specifically?
It often comes down to how specific distros configure things like Wayland compositors or how they handle graphics drivers. Those can easily conflict with the assumptions the Flatpak runtime is making.
Gotcha. So that explains why the forum consensus leans so heavily toward the AppImage format.
Right, because an AppImage takes a totally different architectural approach. It doesn't rely on an external runtime or those restricted namespaces.
It's all just bundled together, right?
Exactly. It statically links or bundles almost every shared library the app needs. So the MLT Multimedia Framework, FFmpeg, the QE libraries, it's all shoved into a single, compressed, executable image. It has everything in its belly.
Which is awesome because you just bypass the host system's package manager entirely. You download one file, make it executable, and just double-click it.
Yep, it contains its own universe. And because it's not sandboxed, the integration with GlaxSubmit works flawlessly. The host system's processes can actually see each other.
And I noticed too, you can have like Kdenlive version 23 sitting in one folder, and then the beta for version 24 in a totally different folder, and they don't break each other.
Which is a huge deal for a production environment. I mean, you do lose the automated updates from a package manager, but most professionals prefer that manual control anyway.
Right, you lock in a version that you know is stable for your current project, and you don't dare touch it until the render is done.
Exactly. But here's the critical pivot. App images are fantastic for using the software, but they're still compiled, optimized binaries.
Right. They solve the deployment problem, not the editing problem.
Exactly. If you want to modify Kdenlive, like if you want to fix that rendering bug we talked about, you can't do it inside an app image. You need the raw source code.
Which brings us to Git and platforms like GitHub. And we have this really interesting Stack Overflow thread in our sources where a user, Kevin Wheeler, breaks down the difference between just downloading a repo as a ZIP file versus actively cloning it.
And it might seem like a minor semantic difference if you're a casual user, but it completely changes your relationship with the code base.
Yeah, I'll be honest. I used to think hitting download ZIP was totally fine. I mean, I'm getting the code, right?
A lot of people think that. But the Stack Overflow explanation is really clear. A ZIP file is just a dead snapshot. You're getting plain text files representing the state of the code at that exact millisecond.
Right.
What you don't get is the .git directory.
And what makes that directory so important?
The .git directory contains the entire topological graph of the project's history. It has every single commit, every branch, the cryptographic hashes linking the files over time, and all the metadata about who made which change and why they made it.
Oh, wow. So downloading a ZIP is kind of like, I don't know, getting a printed photograph of a car. But cloning is like getting the factory blueprints, the prototype history, and the tools to actually build it.
That's a perfect analogy. Without the clone, you can't run operations like git blame to see who wrote a specific line of code. You can't make a feature branch. You're completely disconnected from the project's actual life cycle.
So, okay, let's say we've cloned the repository. We've got the history, the context, the raw C++ files, but now we hit a wall because a folder full of C++ text files doesn't actually edit video.
No, it doesn't. You have to compile it.
Right. And this raises a massive question. Why on earth would a normal user go through the absolute agony of compiling a huge desktop app from source, especially when we just said the app image works so perfectly?
Well, the Linux Reddit thread in our sources gets deep into this specific agony.
Yeah.
And there are actually very pragmatic reasons to do it.
Like,
Well, if you're actively developing a patch, you obviously have to compile to test your own code. Or maybe you're running on like an obscure hardware architecture, maybe a RISC-V workstation, where pre-built binaries just don't exist yet.
okay. Or I guess you might be trying to dodge an overly strict distribution maintainer. Like, user Nothinusberg mentioned that Debian's stable branch is legendary for holding back packages for years just to ensure system stability.
Exactly.
Yep.
So if Kdenlive drops a huge new feature that needs, say, version 7.38 of the MLT framework, but Debian is still shipping version 7.2a, you're just stuck.
Right, you're at their mercy.
Compiling from source lets you bypass those Debian gatekeepers. You take on the headache of dependency resolution, but you get immediate access to the bleeding edge features.
That makes sense. But the thread also highlighted this really funny, pervasive myth in the Linux community about compiling. The myth of local optimization.
Oh, right. The Gen 2 mindset.
Yeah. There's this subculture that totally believes if you pass these super aggressive flags to the GCC compiler, like Nexo3 or NixMarch Native, that you'll somehow unlock these hidden performance reserves, and your app will run insanely fast because it's tuned directly to your CPU.
And a user in that thread, whose account is deleted now, just dismantled that idea so brilliantly.
I thought that was hilarious.
Right. I mean, compiler flags do optimize instruction sequencing, sure, but they do not change the algorithmic complexity of the software itself.
Right. Like, an application's bottleneck is almost never the CPU failing to process instructions fast enough. It's usually stuff like I/O latency or bad memory allocation.
Exactly. The user made this great point that highly optimized code crashes on the exact same bugs as unoptimized code.
An optimized memory leak is still a memory leak.
Exactly. If Kdenlive has a memory leak in the timeline engine, compiling it with Nacho 3 just means your system's going to run out of RAM slightly more efficiently.
That's so funny. It doesn't fix the architectural flaw at all. So you don't compile a desktop app to make it faster. You do it to change its behavior or fix a missing dependency.
Right. And that brings us to the most dangerous part of the whole process.
Uh-oh.
Yeah. If you decide to compile, how you install the resulting binary can literally destroy your operating system.
Wait, seriously?
Oh, yeah. And the main culprit is a command that's been in Linux tutorials for decades.
Yeah.
Make install.
Which sounds so harmless. You've run make to build it and make install to place it. What is actually happening under the hood that makes it so destructive?
So when you run make install as root, the build script just blindly copies the compiled binaries and libraries straight into the host system's root directories, like Acerbin or Acerlib.
Okay.
And it does this without telling the system's package manager. So apt on Debian or pacman on Arch, they have no idea those files are there.
Oh, I see. Because the package manager maintains that strict internal database of every file, right?
Yeah.
So it knows how to handle updates.
Exactly. So make install acts like a rogue agent. It just dumps files everywhere.
Yeah.
And because the package manager doesn't know about them, uninstalling the software later is an absolute nightmare. You just end up with orphan files everywhere.
But how does that actually break the OS?
It causes this catastrophic issue called shadowing, which breaks the dynamic linker.
Shadowing. What does that mean?
Okay, let's say you compile an experimental version of a core multimedia library to test a Kdenlive feature, and you make install it into userlocalib.
Okay, got it.
Then, a week later, your package manager updates the official stable version of that same library in userlib.
Right.
The next time you launch any app that needs that library, the dynamic linker goes searching for it. But because userlocalib often has a higher precedence in the search path, it finds your experimental rogue library first, and it tries to load that instead of the safe system one.
Oh, wow. And because that rogue library might have totally different, application binary interfaces, ABIs, the application just instantly crashes.
Exactly, it's segfaults. The rogue file is literally shadowing the legitimate file. User A. Wendell H. noted that this is exactly how users accidentally destroy their entire graphical interface. They shadow an Xorg or Wayland library, and when they reboot, they just get a black terminal screen.
That is terrifying. So what's the golden rule here? How do you avoid the black screen of death?
The absolute rule is never, ever let make install touch the system-wide Esther directory. Never.
Good to know.
If you're developing locally, you can configure the build to install into your home directory, like .localbuilmin. That way, if you break something, it only ruins your user profile. The host OS stays pristine.
Right, keep the blast radius small. But the Reddit consensus also pointed to a more elegant way to do system-wide installs, right? Using package scripts.
Yeah, that's the professional way to do it. Instead of letting the build script dump files, you use tools like Arch's pkgb build, Slacware's spubkg, or Debian's jeckinstall.
And what did those do exactly?
They act as interceptors. They let the make install process run, but they redirect all the output into a temporary staging folder. Then they compress that folder into a standard package format, like a .deb file, attach the metadata, and hand it back to you.
Oh, that's brilliant. So you wrap the rogue agent in official credentials, and then you just install that package normally. The system tracks the files, and you can uninstall cleanly.
Exactly. It's basic package management hygiene.
Okay, so assuming we respect the hygiene, let's look at what it actually takes to compile Kdenlive specifically. Because looking at their build.md instructions on GitHub, this is not a weekend project for a beginner.
Not at all. The dependency tree is absolutely massive.
Right, because Kdenlive is basically just a graphical front end layered over a bunch of heavy backend engines. The docs say that as of version 24.12, they completely dropped support for Qt5, so you have to compile against the new Qt6 framework, which handles all the GUI elements and cross-platform stuff.
And you also need KDE Framework 6 for the desktop integration, file dialogues, all that. But the real beast, as you mentioned, is MLT.
The Media Lovin' Toolkit.
Yes. That's the engine that actually interprets the timeline and renders the video. The build instructions require MLT version 7.38.0 or higher. But Kdenlive pushes the boundary so hard that they often rely on unreleased API changes in MLT.
Meaning your distro's prepackaged MLT is almost definitely too old.
Exactly. So before you even start on Kdenlive, you have to clone the MLT repo and compile that from source. And MLT depends on FFmpeg, audio resamplers like SOX, image libraries. It's a recursive nightmare.
A recursive nightmare of dependencies. I love that phrasing. And you're not even just typing make anymore, right? The docs mention CMake and Ninja. Why the shift?
Well, CMake is a meta-build system. It doesn't actually compile anything itself. It scans your system, hunts down all those massive Qt and MLT dependencies, checks your compiler, and then it generates the actual build scripts.
Got it. And Ninja?
Ninja replaces standard make because it's hyper-optimized for parallel builds. It distributes the compilation workload across all your CPU cores way more efficiently, which drastically cuts down the build time for huge C++ projects.
It's literally industrial-scale software assembly. And then there are the optional modules, which sound even crazier. Like, if you want AI motion tracking in Kdenlive, you have to link against OpenCV. But OpenCV doesn't include the tracking modules by default. They're locked in a separate repo called OpenCV Contrib.
Right. So now you're cloning two OpenCV repos, injecting the contrib modules into the CMake config, compiling OpenCV, recompiling MLT so it sees the new OpenCV stuff, and then finally recompiling Kdenlive.
It's exhausting just talking about it. The level of systems architecture knowledge required just to get a working binary is insane.
It really is.
But, okay, let's say you do it. You resolve the dependencies, you master CMake, you write a brilliant patch that fixes a bug, and you're ready to contribute your code back to the project. You've won, right?
Not even close.
And this is where we hit a massive paradigm shift, because having the compiled code is just the technical requirement. It does not guarantee your code gets accepted.
Exactly. Open source is not this pure meritocracy where valid syntax automatically gets merged. It is a deeply complex, living social graph.
Right. And the excerpts from the book Free Open Source Software Development really break this down sociologically. They look at how different open source communities structure themselves, and it turns out the community structure usually mirrors the software architecture.
Yes. They contrast the Mozilla model with the FreeBSD model. So Mozilla, the folks behind Firefox, they're surprisingly rigid. It's a strict hierarchy. You can't just push code. You submit patches to module owners who have authoritative control over specific chunks of the code base.
And they have super reviewers too, right?
Yeah, super reviewers with cross-module authority to enforce global standards. They even have release engineers who manage the temporal state of the repo, using terms like thawed, slush, and frozen.
Like literally freezing the code.
Basically. During a frozen state, they lock the repository down to only critical security patches to guarantee stability before a release. It operates very much like a traditional corporate engineering firm.
But then FreeBSD is totally different. The book describes them as more egalitarian, almost democratic. Yeah. They have a core team that's elected by the active committers.
Right. And getting commit privileges, the right to push code directly, is governed by this informal apprenticeship system. A senior committer mentors you, reviews your patches until you prove not just your technical chops, but that you fit the community culture.
Which is fascinating, but I think the most revealing part of the book is the case study on the Videoland project, the VSC media player, guys. This study completely dismantles the idea that being a coding genius is enough to get influence in an open source project.
It's a brilliant study, because Videoland didn't start on the open internet. It started inside the École Centrale Paris, the ECP University. The core devs weren't anonymous avatars. They were engineering students living in the exact same dormitory.
They ate together, went to class together, coded in the same room.
Exactly. That physical proximity created incredibly dense, high-bandwidth social bonds. So when the project finally went open source and invited external developers from the internet to contribute, those external devs hit an invisible wall.
Right, because they could read the code, but they couldn't read the social dynamics of the dorm room.
Precisely. And the researchers identified a crucial distinction here. Technical expertise versus panoptic expertise.
Panoptic expertise. Break that down for me.
So an external developer might have immense technical expertise. They might be a world-class C++ optimizer, but they lack panoptic expertise. Panoptic expertise is the holistic awareness of the project's current state.
Like knowing who's working on what.
Exactly. It's knowing that developer X is currently refactoring the audio subsystem, or that module owner Y is totally burnt out and ignoring emails right now. It's knowing the unwritten goals of the next release.
So if I'm on the outside, getting that panoptic knowledge is brutal. I have to read years of mailing list archives, lurk on IRC channels for months. But if I'm a student in the dorm, I just get it by osmosis. I ask the lead architect what's up while we're making coffee in the hallway.
Which led to the emergence of what the researchers called hubs. They noticed that the external documentation and website maintenance weren't being handled by the core architects or even the best external coders. They were being managed by first-year ECP students.
The freshmen. Why the freshmen?
Because even though they couldn't rewrite the core video streaming algorithms, their physical presence in the dorms gave them massive panoptic expertise.
Oh.
They knew everyone. They heard every conversation.
Oh, they were social routers?
Exactly. If an external developer submitted a brilliant patch to the mailing list and it got ignored, they didn't know how to push it without breaking a social norm. But they could message a freshman hub on IRC. The hub would literally walk down the halls, knock on the senior dev's door, and say, "Hey, look at this patch."
That is amazing. They facilitated the flow of information so nobody lost face. They bypassed the hierarchy using informal social capital.
Yes. So bring that back to Kdenlive. If you compile the code and want to submit a patch, you aren't just uploading text to a server. You have to figure out who the hubs are. You have to navigate the IRC chats, understand the unwritten review process, build friendships.
The friction is immense, both technically and socially.
Immense friction. And that friction creates this huge pressure within user communities for easier ways to modify the software. People want to build custom tools without enduring C++ compilation and open source politics.
They want a scripting layer.
Exactly. Which brings us back to the KDE Discuss forums, where a really contentious debate broke out about Kdenlive's extensibility. Users like UltraDerek and Einar were literally begging for a Python or Lua API.
Yeah, they want the software to expose its internal functions to a high-level scripting language. And Einar points out that the creative industry is rapidly adopting AI and automation. Waiting for the core dev team to build every niche feature is just unsustainable.
Right. Another user, Don't Bother YT, gave a really specific example. They wanted an audio-reactive image plugin. Sort of like how Discord highlights a user's avatar when they speak. They want an image on the video timeline to scale or glow based on the waveform of an audio track.
Which, right now, in Kdenlive, means manually keyframing the scale effect by hand to match every audio peak. It's incredibly tedious. They just want to write a 10-line Python script to bind the audio amplitude to the image scale.
But the developers, specifically Ron and Micah, push back against this with surprising ferocity.
Why? Why block a Python API?
Because they're dealing with the architectural reality of a legacy codebase. Micah stated bluntly that Kdenlive's priority is absolute stability, not chasing buzzwords. A video editor's primary contract with the user is that it will render the timeline without crashing.
And injecting a Python runtime into a real-time MLT rendering pipeline.
It introduces massive latency and memory safety risks. Ron was very focused on the lack of concrete specs. When users vague post about wanting AI integration, Ron refuses to build a massive speculative architecture. He literally said they aren't going to build a general-purpose NLP oracle just so someone can write a script to make the screen flash red.
Right, he's guarding against engineering debt. And he pointed out that plugin interfaces already exist, like the FreeOR API for video effects.
True, but the users aren't asking for low-level pixel shaders. They want structural control over the timeline, placing clips, generating assets.
It's a total deadlock. Users want high-level orchestration, devs are offering low-level pixel math, but then Einar drops a concept into the thread that completely changes the game.
Yes. Einar introduces the Model Context Protocol, or MCP.
The pivot to MCP, which essentially makes the whole Python API debate obsolete.
It really does.
Yeah.
Einar suggests that they don't need Kdenlive to build native AI tools. They just need it to expose an MCP server so external AI agents can connect to it.
So we're moving from writing custom scripts to delegating tasks to AI agents, but what exactly is MCP under the hood? Like, why is it so revolutionary?
Well, the article from the Wireflow blog, Best MCP Server for Video Editing Tools in 2026, really lays this out. Historically, if you wanted an AI agent like Claude to control an app, you had to write custom middleware. You had to teach the AI the exact syntax and endpoints of that specific app's REST API.
Right. My favorite analogy for this is that connecting an AI to a traditional API is like trying to order at a restaurant. But you have to learn the specific language of the chef, figure out how the kitchen is laid out, and basically cook it yourself.
That's a great way to put it. If the app updates its API, your integration breaks immediately. MCP, on the other hand, is an open standard. It's a universal communication protocol between an AI client and a software application.
Like a USB plug-and-play standard, but for large language models.
Exactly. The application hosts an MCP server. When the AI connects, the server broadcasts its capabilities using a standardized schema. It exposes its tools. So the server might say, I have a tool called TrimClip. It needs a file path string, a start time float, and an end time float, and it returns a Boolean.
And the AI reads that menu and just knows how to order. No custom training needed. I tell the AI, trim the first 5 seconds off the intro video, and the AI formats the exact JSON payload required and fires it at the server.
The interface suddenly becomes conversational. And the Wireflow blog shows how fast this ecosystem is moving. Developers aren't building plugins for specific NLEs anymore. They're building standalone MCP servers.
Right. The blog ranked Wireflow as the best overall because they abstract multimodal workflows into single tool calls. So instead of the AI calling separate tools to write a script, make a voiceover, and grab stock footage.
Wireflow exposes one tool like Generate Commercial that triggers a whole pipeline on their cloud infrastructure.
But what if I have sensitive footage? The blog mentioned Kinnicut as the best local option. It's basically a locally hosted wrapper for FFmpeg.
Yes, which sounds terrifying at first.
Giving an LLM direct access to a command line tool like FFmpeg? Oh yeah. If it hallucinates a destructive flag, it could wipe your hard drive. How does Kinnicut handle that?
Strict pre-flight validation. It doesn't pass raw strings to the shell. It exposes 87 highly specific tools, like concatenate videos. When the AI calls a tool, Kinnicut parses the arguments, validates the file paths against a strict sandbox directory, and constructs the FFmpeg command internally. It gives you local processing power with total guardrails.
We also saw ShotStack for cloud rendering and Reap, which is amazing for repurposing content. You pointed out a 3-hour podcast, and its tools use semantic search to clip the best parts, add captions, and even dub it into other languages.
There's also Fall.ai for access to massive generative models and Cloudinary for asset management. It's a huge landscape.
But using pre-built servers is just the start. The Neural Maze Substack article, How Real AI Engineers Build MCP Servers, gives us the blueprint for building completely custom setups. They built the Kubrick project using the FastMCP Python framework.
Right. FastMCP handles all the messy async communication automatically. And the Kubrick project is a great example because it leverages the 3 foundational primitives of MCP: resources, prompts, and tools.
Let's break those down. Resources first. In MCP, a resource is just data the server exposes for the AI to read. But how do you expose a temporal medium, like a video, to an LLM? You can't paste an MP4 into a chat window.
This is where their architecture is so smart. They use a framework called Pixel Table to process the videos. When a video is ingested, Pixel Table samples the visual frames, extracts the audio, runs speech recognition for a transcript.
And it runs the frames through a vision encoder, like CLIP, right, to generate vector embeddings. So the video becomes this highly structured, mathematically searchable database.
Exactly. And the MCP server exposes the metadata of those indexes as resources. The AI connects, reads it, and knows, I have access to a database of 5 specific corporate training videos.
Then you have prompts. The Kubrick team moved the prompt management inside the MCP server using an evaluation framework called OPIC, instead of hard-coding the prompts into the client. Why is that better?
Because if you update a tool on the server, but your prompt is stuck on the client side, they drift out of sync. By keeping prompts on the server, the AI just requests the prompt template when it connects, guaranteeing the instructions perfectly match the available tools.
Smart. And finally, the tools themselves, the executable functions. Kubrick defines retrieval tools like get video clip from your SIR query.
This is their RG implementation, Video Retrieval Augmented Generation.
Right. So I say, find the clip where the CEO talks about Q3 revenue. The AI calls the text query tool. The server converts my text into an embedding, searches the pixel table transcript and frame data, finds the highest semantic similarity, and returns that exact clip.
Or if you upload a photo of a product, it calls the image query tool and finds exactly where that product appears in the video. It traverses vast amounts of unstructured video with pure mathematical precision.
It's incredible. But retrieval is only half of it. How do you integrate those AI-selected clips back into a real editing workflow? For that, we looked at the Video Editing MemCP server by AugmentCode.
Right, which integrates the Video Jungle API. Imagine a developer who records a quick screen capture of a new feature. Instead of opening Kdenlive, they just stay in their code editor and tell their AI assistant, make a 30-second demo of this authentication flow.
The server takes that command, uses Video Jungle to semantically analyze the screen recording, finds the UI moments, and maybe even grabs supplementary clips from the local macOS Photos app. But the key is the output. It doesn't just render a flat MP4 file, right?
No, because that would be a dead end. If the AI messes up a transition on a flattened file, you can't fix it. Instead, the server uses a tool called Edit Locally, which generates an OpenTimeline IO project file.
Which was developed by Pixar, right? It's just a structured JSON file that represents the editorial cuts, the in and out points, the transitions without embedding the media itself.
It is the ultimate bridge. The AI does all the grueling semantic labor of finding the best takes and assembling the rough cut, and outputs the open timeline IO file. You drag that file directly into DaVinci Resolve Studio.
And the timeline just populates instantly with your original high-res media. You keep total non-destructive control to color grade or tweak the audio.
This completely solves the problem the Kdenlive devs were worried about. You don't compromise the stability of the core C++ app. You use MCP as the translation layer and OpenTimeline I/O as the data bridge.
Okay, so we've got retrieval and assembly handled. But what if the workflow needs brand new pixels? Like the AI needs a B-roll shot that just doesn't exist anywhere in the database. The MCP tool has to call a generative engine.
And right now, the absolute cutting edge of open source video generation is the WAN Foundation models by the WAN team over on Hugging Face.
The WAN 2.1 and 2.2 models, and these are built on the diffusion transformer architecture, or DIT. How does a DIT differ from the older UNet models we're used to?
Well, a unit essentially scales an image down into a compressed latent state and then scales it back up, trying to denoise it. But a diffusion transformer takes a massive cue from large language models.
Meaning what? It uses tokens.
Sort of. Instead of processing the image as a continuous grid, the DIT chops the latent space of the video frames into discrete patches, just like an LLM chops text into tokens. Then it applies self-attention mechanisms to those patches across space and time.
Oh, which allows the model to really understand how objects should move across frames. That's why we see so much less temporal flickering now.
Exactly. And the efficiency is disruptive. They have a 1.3 billion parameter model that only requires 8.19 gigabytes of VRAM. You can run that on a consumer laptop, driven entirely by an MCP tool call.
And they aren't just generating random fever dream hallucinations anymore. They offer insane deterministic control, like the first last frame to video feature.
Yes, you give the model a starting frame, an ending frame, and a text prompt, and it hallucinates the entire sequence to connect them.
But the math there is crazy. What if my start image is a 16.9 landscape and my ending image is a 4.3 portrait?
The neural network will fail because it expects a perfectly uniform grid of patches. The Hugging Face docs outline the exact pre-processing required. First, the starting image undergoes aspect ratio resizing. The system scales the width and height until they are perfectly divisible by the DIT's required patch size, usually multiples of 16 or 32.
Okay, and then the ending frame has to be forced to match that exact matrix. So it does a center crop resize, scaling the ending image so the smallest dimension matches, and just aggressively cropping the overflow.
Right. Only when both images are identical dimensionally can they be fed into the DIT. But the real apex of control here is V, controllable generation.
Because text prompts are ambiguous, VE lets you constrain the generation with secondary inputs, like depth maps or skeletal poses, and the core mechanism is the mask rule.
The mask rule is absolute. When you pass a video and a condition map into VDE, you pass a binary mask. Any pixel map to black says, do not alter this area, preserve the source. Any pixel map to white says, this area is zone constrained, generate new pixels here.
Which is the engine behind OneAnimate. It basically automates high-end VFX, like animation mode. If my MCP server has a static image of a mascot and I want it to wave, I just provide a pose video, which is just moving skeletal key points on a black screen.
And the OneAnimate pipeline takes the static image, maps it to the key points, and synthesizes entirely new frames to make the 2D mascot execute the motion perfectly.
But replacement mode is mind-blowing. Say an AI needs to update a training video because an actor left the company. You take the original video, extract the skeletal key points from the old actor, and provide an image of the new actor.
And crucially, you generate a binary mask video, tracking the old actor's silhouette. Applying the mask rule, the background is black preserved. The silhouette is white, unconstrained.
The DIT analyzes everything, follows the skeletal constraints, and diffuses entirely new pixels only inside the white mask. It flawlessly replaces the actor, matching the original lighting and camera movement. And an LLM can trigger this entire sequence of compositing math just from a text prompt.
The architectural distance we've covered today is staggering. We started with the manual labor of the old paradigm wrestling Flatpak namespaces, compiling C++ dependencies, and navigating open source hierarchies just to add a simple feature.
We saw how that friction drove the need for Python scripts and how the developers pushed back to protect core stability. And then we saw how MCP beautifully resolves all of that tension.
By standardizing the interface, MCP decouples the AI logic from the software mechanics. We moved from writing code to building fast MCP servers that turn video into semantic vector databases.
Right, using Open Timeline I/O to bridge into professional workflows and WAN diffusion models to generate pixels on command using complex masking math. We went from manually turning wrenches to orchestrating a symphony of AI agents.
But, this leaves us with a really profound architectural question. For 40 years, software evolution has basically been graphical user interface evolution. Apps like Kdenlive are triumphs of GI design, complex timelines, panels, toolbars.
Right, all designed to expose functionality to human fingers.
But as MCP becomes the universal standard, as software increasingly exposes its capabilities as standardized JSON schemas designed for LLMs, rather than buttons for humans, will the traditional GUI eventually become a relic?
Wow. I mean, if the most efficient way to edit a video is to just tell an AI to query a database, assemble an Open Timeline I/O file, and trigger a diffusion model, what purpose does the timeline window even serve the user anymore?
Exactly. If the backend is completely accessible via natural language, the app becomes an invisible utility layer. The user interface of the future might not have toolbars. It might just be an empty chat box. The software we spend so much time compiling and modifying today might just recede completely into the background, operating silently under AI orchestration.
It's a radical reimagining of how we interface with computing. The era of the mechanic tinkering under the hood is giving way to the era of the director orchestrating the machine. The software is becoming invisible, and we're all just learning how to speak its new language. Something to think about next time you double-click an icon. Thanks for joining us on this deep dive. We'll catch you on the next one.